Okay, so it's a great pleasure to introduce our next speaker on this mechanics session of this afternoon. This is Sarah Hormozi from Cornell University. Sarah visited Brasilia some time ago. It was a great visit. She gave excellent talks, and I'm sure her talk now is also going to be excellent. So I was very happy to find her again and get her to attend our conference. So I'm very happy that she accepted. So Sarah, thank you very much for coming. You can start sharing your screen and starting your presentation. Thank you.
So I am not allowed to share my screen. Would you please?
True. Yeah. I forgot about that. Sorry about that. So where are you, Sarah? Make co-host. There you go. So okay. Now you should be able.
Yeah.
Good.
Okay. Thank you very much. Am I audible? Is everything okay?
Yes, we can hear you. Yeah, thank you.
And the screen, you have the screen as well?
We have the screen as well, yes.
Okay, great. So hello, everyone. First of all, thank you very much, Yuri, for inviting me. And Brasilia always brings back good memory. I visited there in 2011. And it was I enjoyed my visit very much. This is going to be virtual, and I look forward to visiting Brazil one more time, maybe in near future. Thanks for having me. Today I'm going to talk about the slurries of complex fluids and the rheology, fluid mechanics, and microstructure. I would like to acknowledge the assistance of several graduate and undergraduate students and several fantastic scientists that I had the pleasure of working with and having their mentorship as listed here. And also I would like to acknowledge the financial support of several agencies and universities for this work, and everything is in this acknowledgement slide. With that, this is the outline of my work. I will start with introducing the concept of slurries of complex fluids in natural and industrial settings. I will talk about the rheological behaviors and how we can establish scaling laws for them. And finally, I will show how we can make use of our knowledge in rheology and fluid mechanics to address some of the industrial and natural problems. And I will talk about part 3 if the time allows me, because we might go over time by just the first 2 parts of the talk. So, in many industrial and natural problems, we are dealing with dense suspensions that are particles with a wide range of sizes, all the way from colloidal to non-colloidal, non-Brownian particle size, suspended in a viscous liquid. And often the fine colloidal particles interact to form a non-Newtonian matter, which itself drags along larger non-Brownian, non-colloidal particles. And this is what I mean by the slurries of complex fluids or non-Newtonian slurries in this talk. And examples are frequent around us. For example, mud that we have in mudslide, landslides, submarine avalanches is a form of complex slurry, or biomass feedstock, or concrete. And in all of examples, we're dealing with a complex background fluid which has larger non-Brownian particle in it. So I would like to show you a couple of slides about the significance of such material. On natural front, natural disasters cost the United States dozens of lives and millions of dollars in lost property every year. And in this picture, you're looking at the mudslide that occurred close to Santa Barbara in January 2018. After a period of heavy rainfall season, a large volume of water mixed with soil and caused it to liquefy and move down the hill. So you can see what happened after this disaster. And as a result, more than 20 people died, and more than 500 homes got destroyed, and about 1,000 yards of Highway 101 got covered with debris. Well, I was visiting the University of Santa Barbara at that time, and I remember that it took them 1 month to clear the highway. So when this kind of tragedy occurs, we ask ourselves this important question: that can we predict the initiation of mudslide or landslide to avoid or reduce the impact of natural disasters? And when it occurred, can we predict the flow dynamics and the runout to help people? So this is one motivation for studying such materials. Another one is on the environmental front. As you can see in this, so concrete is as I mentioned, concrete is a non-Newtonian slurry. And in fact, concrete is the second most consumed substance on Earth after water. And a mixture of cement and water and sand and gravel produces a concrete. And cement production itself is the source of about 8% of carbon dioxide emission in world, which is not good news. And to reduce this carbon footprint impact, the concrete industry use ash and sand and gravel instead of cement to produce concrete. But the slurry of sand and ash and cement is more viscous than the viscosity than the slurry of cement itself, and it brings challenges to industry when they want to build a huge construction and mix and pump concrete in that amount. And I'm going to come back to this slide and provide some resolution for industry. Another important application on energy front, in the US, more than 50% of the gas and oil production is the outcome of hydraulic fracturing, in which an engineered suspension, which is the mixture of the fracking fluid and sand, which we call it proppant, is designed and pumped in the well with high pressure and rate. It causes a fracture, and when the pressure is released, the grains of sand are left behind to support the fracture. And then hydrocarbon can flow through this porous medium, and it increases the efficiency of the reservoir. However, oil industries have included recently the cyclic pumping of sand or proppant into the frac fluid. The idea is to transport these porous pillars into the fracture and achieve a desirable configuration such that hydrocarbon not only now can flow through these porous pillars, but also through the space between them. And it substantially increases the efficiency of the reservoir. So in this configuration, what we have the fracture, which is supported by these pillars of proppant, and these pillars are porous. So it's just that we are replacing the continuous porous medium with this kind of pillars and the open space between them. So, but we know that when we add a pulse of particle in a fluid in flow, the pulse of particle disperses. And the question is that what is this dispersion, and can we tune the dispersion by using the rheology of the background fluid to come up with the structure or configuration that we want, and we can support the fracture with this configuration, but also we get the maximum efficiency of reservoir. So if time allows, I come back to this slide as well and provide some fluid mechanics solution. So, so in all of the problems that I've introduced, there exist three fundamental steps to be taken to address them. For example, suppose that I want to solve the dispersion of solid in a fracture. Well, we have to write down the second law of Newton. And in order to close the governing equation of motion, we have to understand the rheology, that namely, what is the response of material, how the material deforms under the action of shear stresses and normal stresses that we impose on the material. So that allows us to close the governing equation. And also if we want to, attune the rheology to get, for example, a certain amount of dispersion, as I talked, we need to understand what is the link between the rheology and the underlying microstructure that develops in a material due to the relative motion of particles and fluid with respect to each other. So today I'm going to talk about the rheology, and if you have any question about the microstructure, I would be happy to answer that as well. So let's talk about the rheology. So this is what we have in reality. As I mentioned, we have dense suspensions that are particles with a wide range of sizes suspended in a viscous liquid. As you can see here, the key variables are density ratio between the particle phase and solid phase, particle shape, particle size, and volume fraction of particles. And as far as forces are concerned, we are dealing with hydrodynamic forces, contact forces, and colloidal forces. And you can see that it is very complex, and establishing scaling laws is very challenging here. However, I want to make two assumptions. I want to assume that what if we did not have any large particles, non-Brownian, non-colloidal particles in the system, and we just had these fine colloidal particles? What is the rheology of the material? And this is colloids, basically. And I want to consider another scenario in which we don't have any colloidal particle in the system, but we have these large non-Brownian particles in a viscous liquid. And I want to ask, what is the rheology of this material? And then can we combine our knowledge from the rheology of colloids and rheology of Newtonian suspension to understand what the rheology of the Newtonian slurry is? So, so in colloids, colloidal particles interact through surface forces, thermal forces, and contact and hydrodynamics to form a material that its rheology can be expressed by generalized Newtonian laws or viscoelastic laws. In the case of generalized Newtonian, which is the focus of my talk here, the viscosity as a function of shear rate for this material can decrease by the applied shear rate. We call it shear thinning, so viscosity thins. So the example is mud, for example, biomass feedstock. Or the viscosity can increase as a function of shear rate, and the example is concrete. Or the material can exhibit a yield stress, which is a stress, which is a threshold in a stress, below which there is no deformation in material, and above that, the material deforms as a shear thinning fluid. And the example is again mud. Mud always require a stress, an initial stress to start start its deformation. So this is what. So the takeaway message here is that when we are working with these kind of materials or the colloids, the viscosity, unlike Newtonian fluid that is constant, here the viscosity is a function of shear rate. So please keep that in mind. Now, what about the Newtonian suspension? Suppose that I have these large particles suspended in a Newtonian liquid. These particles are neutrally buoyant, and I apply shear rate to this material. And what happens? So shear stresses and normal stresses develop in the material. And if I assume that there is no inertia in the system and everything is Stokesian, we can say that the shear stress and normal stresses have the viscous scaling, meaning that the scaling is the viscosity of the fluid times shear rate. And the reason that they have normal stresses here is due to the action of particles, due to the presence of particles. It's different from the normal stresses that we get in viscoelastic materials. Here, normal stresses are just due to the presence of particle and the fact that when you shear, particle and fluid particles have to move around each other, and that causes normal stress. And if you look at this form, so viscosity times shear rate is a viscous scaling. Because we are adding particles into the system, we increase the dissipation because of the rigidity of the particles and the fact that when we shear the flow, there is no deformation in the particle phase. To accommodate that extra dissipation, we can consider multipliers here that are called relative shear and normal viscosities, and obviously they should depend on the solid volume fraction. And there is a long history behind calculating this relative shear and normal viscosity, and this graph has summarized all of the work. So it starts from Einstein. So we can see that, I mean, in all of the theoretical, experimental, and computational work, there is one consistent message here, that the relative shear and normal viscosity are function of the solid volume fraction, increasing function in fact, and we get close to the maximum packing volume fraction of the suspension, we get this divergence. And I want to draw your attention to this divergence here, that when we get close to this value, a very tiny change in the solid volume fraction would result in a very huge change in the viscosity of suspension. So this is what we know from the rheology of Newtonian suspension. Now let's see if we can combine our knowledge from the rheology of colloids and rheology of Newtonian suspension to understand what the rheology of non-Newtonian slurry is. So suppose that the fine colloidal particles interact and they form a colloid with a certain rheology that is explained by shear thinning, shear thickening, or yield stress material. And then we have these large particles suspended into this mixture or paste, and we shear that. So normal stresses and viscous stresses appear. And because there is no inertia in the system, the scaling is still viscous. So shear stress and normal stress can be written as viscosity of the background fluid times shear rate. And if we assume that in dense regime of suspensions, everything depends on the geometrical constraint, so we can adopt the same relative shear and normal viscosities as that of Newtonian suspension and close the system. However, we know that here that the viscosity of the fluid depends on shear rate for colloids. But which shear rate? As we add particles into a liquid, we know that particles see a local linear variation in velocity that is different from average shear rate over a larger neighborhood. So I'm going to call that local shear rate. And if we assume that in dense regime of suspension, this local shear rate is mainly controlled by the dynamics of particles, which itself depends on the geometrical constraint, we can say that this local shear rate is linked to the average shear rate with a geometric function that depends on the solid volume fraction. And therefore, the viscosity that I have here is a viscosity that depends on the local shear rate. This is the viscosity that is seen by the particles. And if I know what is this local shear rate, I can close the constitutive laws here. So I have made a couple of assumptions here that we have to test. One assumption that I made is the relative shear viscosity and normal viscosity are the same as Newtonian suspensions. The other assumption that I made was that this local shear rate is a function, is linked to the average shear rate via a geometric function which does not depend on the rheology of the background fluid. We have to test that as well. So to do that, we have performed pressure imposed rheometry. That what we do, we load the suspension of particles and viscous liquid in this annulus, and we rotate it. And there is a plate on top that is stationary. Okay, sorry, not a stationary. It is not rotating. However, it is free to move in a vertical direction. So because the plate is perforated, the fluid can go through, and we impose a pressure on this, and the suspension adjusts its volume fraction by the motion of this plate up and down. And basically, because the plate is perforated, all the pressure that we impose, it's being imposed on the particle phase and not liquid phase. This is called pressure imposed rheometry. I'm sure people who are familiar with the granular media, they know this setup. So in this kind of experiment, what we do, we apply normal stress and shear rate, and we measure what is the final volume fraction of the solid and the shear stress as we achieve a steady state. I always have this slide ready because some of my audience is from the rheology, not granular media. I just want to emphasize that this is the same as the volume imposed rheology. And what we do in nowadays rheometers is as follows. We prepare a suspension which has a fixed volume fraction of solid. So we know what is the volume fraction. We impose a shear rate, and we measure the shear stress and normal stress. So that's what we do. So we impose gamma dot, and we fix gamma dot and phi, and we measure normal stress and shear stress. When we have a pressure imposed rheometer, however, we have this suspension, we make this suspension, but we don't fix its volume fraction because the upper plate can move up and down. So it changes the volume and consequently the volume fraction of solid. And we impose a shear rate. So we impose the pressure and shear rate, and we measure the final solid volume fraction and shear stress. And if you do the dimensional analysis here, you can see that you can come up with a couple of dimensionless numbers that are important. One is the ratio of shear stress to normal stress, and one is the solid volume fraction, of course. And you note that this depends on a dimensionless number that is called J, and it is the viscous stress over the normal stress in the system. And also it is the time scale of microscopic rearrangement of particles in a Stokesian solution or a scan flow compared to the time scale of the flow. So what I want to say is that there's a one-to-one mapping between these two approaches, and they both give us the same law at the end. So it was just an aside slide for those audience who might come from different background. So, okay, what I want to do now, I want to examine the assumptions that we have made. One assumption was that we are allowed to use the same relative shear and normal viscosities as that of Newtonian fluid. So if this is the case, then when we measure the friction coefficient or the ratio of shear stress to normal stress, it should not depend on the rheological properties of the background fluid, but just the ratio of these two, which is the same as Newtonian fluid. So this basically friction coefficient should not depend on the rheology of the background fluid. And this is the result. We have tested that for different fluid with different yield stress and for Newtonian fluid, and you can see that everything collapses on this master curve, meaning that in dense regime of suspensions, the main mechanism that controls the rheology or the main contribution is coming from contact forces and geometrical constraint. Another assumption that we made was that this local shear rate is a function of the average shear rate via a geometric function f of phi. And if we measure this geometric function, we note that in fact, for all of the background suspending fluids that we've used, this is just a function of solid volume fraction. And it's an increasing function. So again, another validation for the assumption that we made that to the leading order geometrical constraint is the most important thing, and it controls the dynamics of particles. With that, we have a law basically to examine any rheology. And today I want to talk about the rheology of concrete or cement. And I want to come up with a shear thickening material and add particles into that to just test this scaling law. So in this picture, you're looking at the suspension of cornstarch in water. Suspension of cornstarch in water exhibits shear thickening behavior, similar to cement and concrete. And I want to use that as a background fluid, and I want to add large particles into that to test the scaling law. Here you're looking at the micrograph of cornstarch in water. You may note that the particles are not spherical. The size is not uniform. So we have a size distribution from 5 micron to 20 micron. And suppose that we make a suspension of this material and we do the rheometry. What we are going to encapsulate or sandwich this solution between two plates. We're going to ramp up the rotational speed of the upper plate, and we measure the torque, and from that we extract the viscosity of this suspension. This is the result. We note that the viscosity at the beginning behaves like a shear thinning material. It achieves a plateau, which is a constant velocity, and after that we get a rise in the viscosity that is the signature of shear thickening material. And depending on what the volume fraction of this small grain is, we get continuous shear thickening. So the rise occurs in a continuous fashion, or discontinuous shear thickening that at a critical shear rate, we get this huge jump in the viscosity. So before adding large non-Brownian particles into this system, I want to talk a little bit about what is the state of art now, about why we get such a huge jump in the viscosity of such materials. And the idea is as follows. If I have particles in a system, for some suspensions, we have repulsive force at the grain, at the surface of the grain, and that repulsive force does not allow contact between the grains. However, as we shear the material, I said that because of the presence of particles, we develop normal stresses also in the material. So at some shear rate, the normal stresses are large enough to overcome these repulsive stresses among the grain. And at that point, the grains touch each other and friction comes into play. And everyone knows that friction is a singular thing. I mean, as soon as you switch it on, mathematically speaking, the governing equation of motion, the governing equations of motion would change, and that kind of changes the whole solution, and then we get this huge rise in the viscosity. So basically, the most today theory about this shear thickening material is the transition from frictionless to frictional assembly of grain at a critical shear rate. So now I want to add large non-Brownian particles into this mixture and see what the rheology is. So as you can see that the red curve shows a suspension that itself was a shear thickening, and it kind of shows a discontinuous shear thickening at this critical shear rate here, and we start adding large non-Brownian particles into that, and we see that this shear rate, the critical shear rate that the jump occurs, would happen at a smaller shear rate. And the reason is that because of adding these large non-Brownian particles, the shear thickening should happen when the local shear rate meets the critical shear rate, that repulsive forces and normal stresses balance each other, which is at a smaller average shear rate in the bulk. So this is basically if I divide this shear rate for the pure suspension by the others, that would basically give me the geometric function f of phi that I talked about. And also, you note that as we add large non-Brownian particles into that suspension, the rheology and the viscosity increases, and that is because of those relative shear and normal viscosities that I explained previously. So now we can basically scale any other study in the literature. For example, here there is a study that people have added large non-Brownian particles to a shear thinning material. So this material shear thins with viscosity. As they add larger particles, you can see that the onset of thinning now advances to a smaller shear rate, and also viscosity increases. So this is the effect of local shear rate, and this one is the effect of the relative shear and normal viscosities. And with a proper scaling, we can basically overlap all of these. If we plot viscosity of suspension divided by the normal shear viscosity as a function of this local shear rate now, we can see all of these curve collapse. Or if we add our large non-Brownian particles into a suspension that exhibits continuous shear thickening, we can see such behavior that is scalable again with the constitutive law or scaling laws that I introduced. We have to just plot the relative viscosity as a function of the local shear rate. And we have done it for the yield stress materials. If you are interested in, I'm going to talk about in detail. But to give you a quick recap, here we have done as follows. So we came up with scaling laws that are applicable to suspensions of large particles into a suspending fluid that is not Newtonian. And all we have to keep in mind that the viscosity that we have to input here is the viscosity that is seen by the particles that depends on the local shear rate, which is linked to the average shear rate by a geometric function f of phi, and we are allowed to use this same relative normal and shear viscosities as that of Newtonian fluids. And with that, I showed you how by adding these large non-Brownian particles to a shear thickening material, we can predict the behavior of the material by having this concept of local shear rate in mind, and also the relative shear and normal viscosities in mind. And this is basically the behavior of concrete that I'm going to talk about shortly. However, I want to pause here and take questions, if any, before proceeding to the next slide. And also, please let me know, Yuri, how I'm doing as far as time is concerned.
Sarah, you're fine in terms of time. So it's 5:45. We started a little bit late, so I guess you still have at least 20 minutes to talk. Does anyone want to ask any question before Sarah proceeds? I can ask a question, Sarah. So you showed in that slide, you show that you can measure the local shear rate experimentally, and I think it was on slide 16 or something, where you plotted that F. Can you tell us a bit more about how do you measure this F?
Yeah, that's a very good question. We have measured this F using different approach, but that plot is related to this one that I'm going to talk about. So one way to measure that local shear rate is to do the coarse grain simulations and calculate the velocity field between the grain, and from that extract the local shear rate. And of course, if we do that, we're going to get a spectrum of shear rate because it's not constant. All I'm doing here is making use of the mean value of that spectrum. So that's one way of measuring that computationally. Also experimentally, we can track, we can add fluorescent dye and track the those fluorescent dyes and calculate the trajectory, and from that extract the local shear rate. Again, we're going to get a spectrum of local shear rate. However, here was a rheological approach. This is how we did it. So suppose that I have a suspension that we add large non-Brownian particles into a yield stress fluid. And so the yield stress fluid's rheology is as follows. We have a yield stress plus a consistency times gamma dot to the shear rate to the power of n-1, which n is the power law index, times gamma dot. Now, what we say here, we say that this, if I want to come up with the rheology of suspension, meaning that the yield stress fluid plus particle, the rheology itself is a yield stress fluid, but now I have to write down this viscosity, this effective viscosity, as a function of local shear rate. So we're going to substitute every shear rate with local shear rate. And then we are going to adopt the same function as that of Newtonian fluid, and we know what is this based on the Newtonian suspension rheology. So now if I say that this local shear rate is this f of phi, this geometric functions time gamma dot, and substitute that here, I'm going to get such relationship. So now what we do, for a volume fraction and an imposed shear rate, we measure this shear stress. So we have everything, and the only thing that is unknown in this equation is this function f of phi. And we extract this by just solving this equation.
And the exponent n as well, right? You don't know, or...
No, we know. So we know the rheology of the background.
Of the background fluid, okay.
So the rheology of background fluid gives us the yield stress, which is tau y, and it gives us the power law index, which is n, and it gives us the consistency, which is kappa. And now what we don't know is the rheology of the yield stress fluid or the background fluid, suspending fluid, if you wish, plus particles that we don't know.
Mm-hmm.
So what we do, we say that, well, this rheology, this viscosity of the paste, the new paste, is a function of this local shear rate. So in that function, I know everything because I know the rheology of suspending fluid, except this gamma dot local, which gamma dot local was this f of phi times gamma dot. So I don't know, therefore, this f of phi. So what we do now, we have this paste, we apply shear rate into that. We know what the rheology of the background fluid or suspending fluid is. So we know n, kappa, and tau y. We adopted this eta s of phi from empirical relationship for Newtonian suspension. So in this equation, because we apply shear rate to the whole suspension of particles and suspending fluid, and we measure shear stress, we know everything except with function, geometric function f of phi, and we can calculate that.
So can you help me with some intuition here? So if phi goes to the maximum packing,
yeah,
I can see that f of phi increases, right?
Right.
So my impression is that as particles get closer and closer, as it is, as your graph is saying, locally the shear field increases because the fluid is constrained. There's a local flow rate that has to flow through the particles, and of course the shear rate will be larger. But as soon as particles touch, I assume that there is no more constraint, geometrical constraint, so the fluid will follow through the pores. Why does it increase? Why does?
Because exactly what you said. So you explained the whole thing here. When
Right.
we phi, we are basically decreasing the surface to surface distance of particles. So local shear rate should go up because of the, if it's, we can talk, so because of what you said. And then as they touch, basically this is jamming, right?
Right.
If all of them touch each other, it's jamming. It's like nothing is gonna move anymore.
That's right.
So nothing is gonna move anymore. There is a divergence here as far as the whole suspension is concerned. But then, yeah, you are approaching that limit that the particles are now fixed and the fluid is going through. It's a porous media now.
Yes.
But as far as suspension is concerned, so the mixture of solid and fluid, that point of view, the viscosity has diverged because now.
I see.
So this is.
Very good, Sarah. I think we can carry on. Let me check whether we have more questions for this first part. No questions here on the chat. So carry on, and we'll carry on with more questions after you finish. Thank you.
Okay. Yeah. So so now I want to talk about the problem that I introduced at the beginning of my talk about the in concrete industry. So what they do in concrete industry, as I said, to improve the carbon footprint, they add ash and sand instead of cement to reduce the amount of cement. So what happens, so they have this cement that exhibits shear thickening behavior, such as like what you are seeing here. And then they add large particles into that, and they get this, this jump in viscosity. So if you keep that scaling law in mind that I talked about, what we do, I mean, based on that scaling law, all we do is by adding large non-Brownian particles, we are changing this local shear rate. So we are changing along this axis. So what it means that I have to move along this black curve. So changing from one rheological behavior to another rheological behavior and seeing such a discontinuous property by just adding large non-Brownian particles, we cannot explain it by the rheological laws that I showed. However, also I showed you when I was talking about the rheology of cornstarch suspension, that when we increase the volume fraction of cornstarch, basically we get this jump. And so what's happening here? So what's happening here, so it seems that when we add these large non-Brownian particles, there should be a mechanism under the action of which the volume fraction of this small grain changes in the suspension. So, and the reason is that, so when we add these large non-Brownian particles, you can see that the small grains cannot come closer than the radius to the surface of these large particles. So therefore, there is always a shell around these large particles in which the volume fraction of the small grains drops. However, the volume fraction of the small grains is constant. Therefore, this drop should be compensated by an increasement somewhere else. So I'm going to call this increasement effective volume fraction of cornstarch, and we can show that this is a function of the initial volume fraction of cornstarch or cement, volume fraction of these large particles, and the ratio, the size ratio of these large particles to the small grains. So this is the assumption. Let's test it. So what we are going to do, we are going to plot this effective volume fraction as a function of the initial volume fraction and the volume fraction of large particles that we add. So we're looking at the rheology of the small grains or cement or cornstarch. And we know that as at some volume fraction, about 39%, 38%, the volume fraction, or maybe I should because I can, okay, so yeah, about 38%, the rheology changes from continuous shear thickening to discontinuous shear thickening. So now if I plot the line of 38% here, anything before this line, below this line should behave like continuous shear thickening, and anything above this line, which is basically these black rheology, should behave like a discontinuous shear thickening. So we start with a suspension of small grains in water at 35% that shows a small shear thickening behavior. And we keep adding large non-Brownian particles, and we see that there's a rise in viscosity. As soon as we pass this line, we get discontinuous shear thickening and discontinuous shear thickening. As soon as the effective volume fraction of the small grains passes the critical shear rate. So, and basically this excluded volume is a confinement effect. You can think of it as this. Initially, we have these small grains in water. We add the large particles into that. As we increase the volume fraction of large particles, the surface to surface distance decreases. So it's like confining the particles and magnifying that effect of effective volume fraction. And we can basically reproduce it by designing a simple rheometry test. This can be also valid if we sandwich the suspension between two plates and decrease the gap between these two plates. And you can see this is an excluded volume in the vicinity of the top and bottom plate. And as we decrease the gap, it's like adding more and more particles or confining more and more the small grains. So at some gap, basically this jump from one rheological behavior to another rheological behavior should occur. And we can basically theoretically calculate that one. It's a very simple thing to do. And we have done this test and we see, in fact, this is the case. So basically at a small gap, we have this continuous shear thickening behavior. And as soon as we pass a threshold in gap that we can calculate it, we get a change in the rheology, the same as the case that we were adding larger particles. So I wanted to just show with this simple experiment that the adding large particles or this excluded volume effect is the same as confinement effect. So now, this is the resolution for concrete industry. They want to operate in regime in which that they don't experience this discontinuous shear thickening, because as I said, a huge jump in viscosity causes lots of problem when it comes to mixing and pumping. So they have to operate in the system by tuning the initial volume fraction of cement and this the volume fraction of ash and stone that they add, and also their size ratio between the cement particle and the sand or ash and gravel, to always make sure that they are operating in this continuous shear thickening regime. And we have basically worked on this constitutive law and scaling laws for suspension of particles in a non-Newtonian fluid, and we are moving it toward having a tensorial framework, and also we are including the effect of inertia as well. So I think with that, I think it's going to take lots of time, more than what I'm asked to. So with that, I would like to summarize my talk. That the takeaway message is that I introduced a scaling law in which we can predict the rheology of a mixture of particles and a fluid that behaves in a complex fashion. And also I showed that how we can take into account the excluded volume or confinement effect to predict if there is a change in the rheological behavior. And we can show this basically, this constitutive law, and do model framework for geophysical flows, thin film flows, or Healy-Shaw scale, those flows that adopt the Healy-Shaw scaling. And with that, I want to thank you. And these are my references. And I would be happy to take any questions.
Thank you very much, Sarah, for this very stimulating talk. It's very nice. So let me see if we have any questions on the chat. So please, if you want to ask a question, raise your hand or write something here on the chat and we will read it to Sarah. Sarah, while people decide whether they want to ask a question, let me ask you another question. Let me open my video. Okay, all right. So you showed at the beginning of the talk actually that there was a scaling for your normal, not normal, but for the normal pressure for the P, which is a viscous scaling that depends on eta of phi times the eta of the fluid times the shear rate. I remember that very famous paper, by Babette and Poulican, where they showed that suspensions can have normal stress differences. So your viscous scaling, is it for the global mechanical pressure? So it is for the third of the trace of these normal stresses. And can you somehow measure normal stress differences and include normal stress differences in your rheology?
Oh, that's a very good question. So when I talked about the tensorial framework, I meant that we can measure we are trying to measure the normal stress differences. There are so many challenges when it comes to these kind of fluids. For example, most of these fluids are blur and opaque. Yes. I've done some X-ray or MRI to be able to measure those fluids. So this is just one component of the normal stress that we've measured here, and that's what I mentioned, that we're working on the tensorial. And this graph is from Elizabeth and Olivia.
Yes, I know this graph very well. Yeah, I read that paper. The experiments that they performed, the way that they measure was via surface curvature, right? So it was a very beautiful, elegant experiment with light I'm not sure whether scattering or just reflection, and then they framed everything, and they realized how the height would change the way that light would be scattered. So that was very elegant, and they realized that in these dense suspensions there is a second normal stress difference and not the first one. The first one is very small and the second one is large, as opposed to elastic liquids. So that was something that was very, very fascinating. So let me see if we have other questions here. So did you work on this experimental setup that they proposed, the one that you showed?
Actually, I worked with them for these results are with Olivier Poulican and
Babette, yeah,
and Elizabeth, right?
Yeah. Okay, all right. Let me see if I have questions here on the chat. No one has raised hand. So I have another question. This is a more general question. So we would all like to have a continuum formulation for these kind of flows. And I think probably the closest that we have is is the mu of K that includes the mu of I and the J effect that you showed there, which is the viscous inertial number, as probably you want to say that. So what do we get from your presentation and the continuum formulation of granular flows? Are we there yet, or what is still missing?
Yeah, that's a very good question. I am trying to pull up a back of a slide because usually I don't speak in the language of granular media because my audience is coming from the rheology background. But okay, here I think I have all of the I have the back of the slide to show. So, okay, I'm going to share my screen again. Can you see my screen now?
Yes.
Okay, so yeah, you're okay. So in that framework, in the language of granular media, we have a dimensionless number that can be I or J. So in inertial granular media, it's I, which is the ratio of the microscopic time scale of the rearrangement of particles to the macroscopic time scale of flow. That is I. But when we have a Stokesian suspension, that time scale, that ratio of time scale is different, and it is given by the viscous stresses to particle pressure if you do the math. And it's just you know that how it works. And then we have this J. But because, for example, in a yield stress fluid, we have another intrinsic stress in the suspending fluid that is now yield stress. We have another dimensionless number here. Let's call it J of Y, and this is the ratio of the yield stress to the particle pressure. So now the effective friction coefficient is the function of this J and JY, or phi, the solid volume fraction, is the function of J and JY. So if I look at the friction coefficient as a function of J, I would realize that it changes with the value of JY as well. And also phi changes. And one interesting thing is that, it is very interesting, is that, so if it was a Newtonian suspension, as I get to small j meaning that, the shear rate almost goes to 0. So we press on a suspension and shear rate is small, meaning that we have maximum packing volume fraction, right? And then we start increasing the shear rate, so then the suspension dilates and becomes smaller. But interestingly, as we increase the yield stress, we can see that we never achieve the maximum packing volume fraction. It is like that there is always a material between the grains that creates solid bridges. Because it's a yield stress material, so when it might not yield, so then if yield stress is really high, then you never achieve the maximum volume fraction.
Volume fraction, I see.
And it happens at a smaller volume fraction, which is very interesting if you're familiar with the shear-induced migration phenomenon.
Yes.
Which means that if you have a yield stress fluid and particles in the center of your channel or part, you never get to maximum packing volume fraction, even if you do it in dense regime. So you always basically have some. You're always lower than the solid volume fraction. It's very interesting. I mean, we're doing experiments on these things, but we are still not there to publish our results. So.
I see. Very nice. Let me see if we have a question or someone has raised a hand. No. So I have a quick final question that you're talking about this shear thickening, and there was for some reason, in some situation there was also some sort of shear thinning, right? That you showed there. So in your experiments, have you noticed any sort of thixotropy on these suspensions?
No, and I purposefully did not, because I purposefully designed a suspension or a background fluid with no thixotropic effect. That doesn't mean that they don't exist in real material or industrial material. It means that I did not want to
deal with it.
Yeah, exactly. So these experiments are all of these experiments are model suspensions with what we want, because everything's the effect of everything is non-linear. And when you have more than one parameter, the non-linear coupling of all of those wouldn't allow us to conclude what really happened in experiments. So we had to be cautious about that. But you're right. I mean, in real life materials, it's very complex, because all of these are present, and the non-linear coupling are there, but we had to just focus on one item.
One item, one at a time.
Yeah.
Very good. So let me just double check whether we have no more questions. And then, no one has raised a hand. Okay, so Sarah, thank you very, very much for your presentation. It was great. Thank you so much for accepting the invitation to participate in our workshop and give this talk. It was very, very nice to see you again. If you want to say something before we finish this talk, you're very welcome.
Well, thank you very much for having me and inviting me. And I am sorry that I was late for a couple of minutes. This is the first week of semester, so many things are going on at the same time.
Okay, and no worries. That's
you all hopefully near future in Brazil. It's one of my favorite countries.
Very good. We should organize something as soon life backs to the new normal. Life goes back to the new normal, right?
Yeah, I mean, you've been such a wonderful host last time, and I really enjoyed my time at the University of Brasilia. I hope that I get a chance again to visit.
Excellent. Yeah, definitely. Yeah. So thank you very much. And I would just like to say that, I don't know if you all received the email. Today is by chance, today is the International Day for Girls and Women in Science. And I chose the 5 speakers of today on purpose to be women, but I did not choose the day because of that, right? It was because Sarah was able to do on the 11th, and then we tried to organize everything, and it happened to be today. So I'm very happy of this very nice coincidence that we had wonderful 5 talks on the day, all given by spectacular scientists, women scientists. And I'm very happy that we praise this beautiful day with the way it should have been done. So I'm very happy about that. And I hope our girls, our women watching this or this video later on will see this as a good example that yes, you can and you should go ahead and you do things probably much better than many men scientists do. So I'm very pleased that it happened this way. So thank you, Sarah. Thank you, Aline, and thank you to the other 3 speakers of the day. So for this very nice coincidence. So I'm very happy and pleased about that. Okay, so Thank you.
Very much. It was a great pleasure to be here.
Very good, sir. Thank you. Okay, so thank you all very much. Hope to see you all again at some point in the next workshop or in some conference somewhere discussing nice things. So all the best to you. Take care and have a nice 2021. Bye-bye.
Bye-bye. Bye.